This is EE698I, Mixed Signal IC Design, and this is lecture number 19. In the last class, we started to look at the Flash ADC, where we saw that to have an n-bit Flash ADC, we need a total of 2 power n-1 comparators, right? And all these comparators operate in parallel, processing the same input, but comparing it with different reference voltages. Okay, so if this is one comparator which processes a fully differential input, say the positive is Vi plus, the negative input is Vi minus, it compares this differential input with a differential reference voltage, which I call say Vr plus and Vr minus. Okay, and it gives a digital output here, right? And in the Flash ADC, we'll have multiple such comparators in parallel. Okay. Now, although in the Flash ADC we have this area overhead, the advantage with the Flash ADC is that it is the fastest ADC we can have, right? Because the time required for entire digitization is the time taken by only one comparator, right? So the delay of only one comparator is what determines the speed of the ADC. Okay, so if you want to have a very high speed ADC, Flash ADC is the way to go. And in a later class, we will see a technique by using which we can further improve the speed of the flash, or we can further improve the speed of the ADC. Okay, and in the last class, we also saw how to generate these differential references. So all we had to do was to have a resistive ladder like this with equal resistor values between VDD and ground. Okay, and this voltage will give me the first positive reference, and this will give me the last positive reference, which I'll simply call R of K. Similarly, to generate the negative reference voltages, we have to have the same resistive ladder between VDD and ground. But here the top one will give me the first negative reference, so on, and the bottom one will give me the last negative reference, right? We also saw the possible implementations for this comparator itself, and we saw that the best solution is to have a regenerative latch based comparator where we have two CMOS inverters connected back to back like this, right? And in this case, we saw that if we have a differential input of delta V, the output will rise exponentially as delta V e power plus t by tau, where this time constant tau depends on this gate capacitance, which I call Cg, and the transconductance G, right? So the output will do something like this. It will rise exponentially and will saturate to VDD. Okay, and of course from this we can clearly see that the gain of this regenerative latch is e power t by tau. Okay, so if say the time available for comparison is some ts by 2, okay, so this point, then the gain is simply e power ts by 2 tau, right? So let me write this to be the gain. Okay, so now we know that the output needs to settle to VDD finally, right? So which means if we have any input which is smaller than VDD by the gain, that is VDD by ts by 2 tau, okay, then the output will rise exponentially, but it will rise slower. And at the end of this time, ts by 2, the output might not have grown and reached VDD. Okay, and here we see that the output here is neither at logic 1 nor at logic 0, right? It is stuck somewhere in between, and this is called the metastable state, And this is usually called the metastability problem in a comparator. Okay. And obviously this is not something we want, because at the output, we expect that the comparator has made a decision so that the succeeding digital logic decodes it as logic 1 or logic 0, right? But here it is stuck somewhere in between. Okay. And obviously the way to reduce metastability, that is to reduce the probability of this metastability, is to make sure that we have a large enough gain, right? And one way to increase gain is obviously to extend this time ts by 2. Okay, so let us say if ts by 2 is longer, then obviously this also would have settled to VDD by this time. Okay, but of course that's not something we want. We want a faster and faster ADC. So which means for a given time ts, the only way to reduce the probability of metastability, right, is to have smaller and smaller time constant, right? And since tau is simply Cg by Gm, and since this is also equal to 1 by Ft of the device, as we go to lower and lower technology nodes, Ft will increase, so the time constant will also reduce. Okay, so the overall gain of the comparator will also increase. Okay? But of course, when you go to lower technology nodes, we are also expected to operate the ADC faster, so even our PS will reduce. So obviously there is some trade-off. Okay, so the bottom line is, to reduce the effect of metastability, we need to increase the gain of the last comparator. Okay, and in the last class we also saw the problem of offset in comparators or in latches, and there were two kinds. So one that arose due to the mismatch in the properties of the transistors itself, which could be the dimensions W by L, nuance aux, or the threshold voltage. Okay, and the offset arising due to these mismatches is called static offset. We also saw that due to the difference in the capacitors at the output, we have dynamic offset. Okay, so let's now see how to deal with this offset. To deal with the static offset, we'll use the information that we know about mismatch. Okay, so you might have learned in your analog circuits course that if we have, let's say, multiple transistors like this, all nominally having the same bits W, in practice, finally, you will see that their bits will all be different, right? So this might be some W plus delta W1, this could be W plus delta W2, this could be W plus delta W3, and so on. Okay, and it turns out that the standard deviation in this delta W is inversely proportional to square root of the area, right? W times L. Okay, and not only for delta W, even for the VT mismatch, that also turns out to be inversely proportional to the area, right? And same with delta beta also, where this mu and Cox is called beta. Okay, and this is also inversely proportional to W times L. And of course, this is known as the Pelgrom's model or Pelgrom's law. Okay, so from this, it is clear that if you want to reduce the effect of mismatch, one obvious way is to increase the area of the device, right? So if we have larger and larger device, the effect of this mismatch will reduce, and we can also reduce the offset of the latch. But obviously, the moment you increase both W and L, the capacitance will also increase, right? So which means the time constant tau that we saw here, that will also increase. Okay, so which means the speed of the latch will also reduce. Okay, so obviously this is not a great solution if you want to have a faster and faster ADC. So let us see if there is a better way to deal with this offset. See, this is our latch, and I'll represent the offset of this latch by an additive source like this. Okay, so now this has no offset, right? And this is our overall latch. Okay, say the input voltage is Vi, so the input to the latch is Vx, right? And Vx is simply Vi plus Vos, right? Now, ideally, we wanted the latch to make a decision of VDD, that is, we wanted to produce an output of VDD the moment Vi becomes greater than 0, right? But here the actual input that goes into this latch is Vi plus Vos. So the latch will toggle only when this is greater than 0, so which means only when Vi is greater than minus Vos, the latch will produce an output of VDD. Okay. Now let us say we want to reduce this offset from Vos to some Vos by A, right? That is, we want to reduce this offset by a factor of A. What can we do? Again, please pause the video and think. So if you want to reduce the offset by a factor A, we want the latch to toggle when Vi is greater than minus Vos by A, right? So which means we need to have AVI to be greater than minus Vos, right? So in this, instead of having Vi, if we have A times Vi, this will happen, right? So what we do is the following. We take the input, feed it to an amplifier with a gain A, right? So that this is now A times Vi, right? And this is the offset here for the latch. Okay. So now the input here, Vx, that will be A times Vi plus Vos, right? And obviously when this is greater than 0, the latch will toggle. So the offset is minus Vos by A, right? And this amplifier is usually called the preamplifier. Okay. So this preamplifier does two things. One, obviously it helps us to reduce the offset by a factor A. And also it increases the overall gain of the latch, right? Because now the overall gain is the gain of the amplifier, that is A, times the gain of the regenerative latch we had, that is this fellow, right? So now the overall gain is A times e power ts by 2 tau. Okay, and as we saw earlier, to reduce the effect of metastability, we need to reduce the gain of the latch, right? So now since we have the preamplifier, the overall gain is also increased. So this will also help in combating the effect of metastability. Okay, although this works and it helps us to reduce the offset by a factor A, it has one glaring problem. That is, this preamplifier here, we have assumed it to be ideal, right? But in practice, this will add its own offset. Okay, so let us now see how to tackle that problem. So this is our preamp, right? And the offset of this preamp can be modeled as a series voltage source, either at the inverting or at the non-inverting terminal. Without loss of generality, I've assumed it to be at the non-inverting terminal. Okay, so let me call it VOS2. So that is the offset of the preamp. Okay. So if let us say this is the input, the output here will be A times Vi minus VOS2. Okay. Now, in principle, if you know what is this offset voltage VOS2, if we add a voltage source, right, with the opposite polarity here, right, then the effect of this offset will be completely cancelled, right? Because here if the voltage is Vi, here it will be Vi plus VOS2. So at this point, it will be simply Vi, right? So in principle, this works, but obviously we don't have an ideal voltage source on an IC. So we'll use the next best thing we have, which is a capacitor that is charged to the correct offset voltage. Okay, so if this is VOS2, then when we have the amplifier connected like this, then we'll have the effect of the offset of the preamp will be completely cancelled. Okay, and please notice that this terminal is not accessible to us. Okay, only these two terminals are accessible. So let me just make it clear. Okay, so only these two terminals are accessible. Okay, and that's why we can't provide the input directly, right? I mean, hopefully that is obvious. So now the question is how to charge this capacitor to this offset voltage VOS2. For that, let's look at the preamp once again. So this is our preamp. So this is the equivalent offset model here, VOS2. Right? Now if we connect the preamp to be in unity feedback like this, right? And if the amplifier has high enough gain, then virtual ground will be enforced. So this voltage will be 0, right? Okay, I think I'd assume the polarity, to be like this, right? This voltage is 0. So this voltage will be VOS2, right? So now if we connect the capacitor here like this, it gets charged to the required voltage of VOS2, right? And that's what we wanted here. Okay, so this is how we can make sure that the capacitor is charged to the correct offset voltage, right? And obviously we don't want to connect it like this all the time because we want to amplify the input also, right? So what we'll do is the following. In one phase, we'll have the circuit like this, and in the other phase, we'll have the circuit like this. Okay, so the overall circuit will look like this, right? So in one phase, we'll feed the input. So let me just slightly push it here. We'll feed the input like this to the capacitor, and in other phase, we'll short the capacitor to ground like this, and we have the offset voltage here. Okay, and of course, in one phase, we'll put it in feedback, right? So we'll have something like this, right? So let's say during phase phi 1, we connect it like this, and during phase phi 2, we feed the input. Okay. Now, obviously, the op-amp will not have an infinite gain, right? So let's see what happens if it has a finite gain of A. So during the phase where we are estimating the offset voltage, we have the connection like this. Right? So if let us say this is some V0, this voltage will be what? If I call it to be some Vy, Vy will be minus V0 by A, right? If the gain is C. Okay, so which means this voltage, it's simply minus V0 by A plus the offset voltage VOS2. Okay, so this is VOS2, right? And this is simply equal to V0. So this is equal to V0, right? From this you can easily find that V0 is A by A plus 1 times VOS2. Okay, so in the next phase, when we put the capacitor in series with the input voltage, we also have the offset here. So we have the circuit like this. This is the input. And in the previous phase, the capacitor was charged to V0, right? So in this polarity. So the capacitor was charged to A by A plus 1 times VOS2. Okay, so the voltage Vy at the input of the preamp, that will be what? That will be Vi plus VOS2 times A by A plus 1 minus VOS2. And this is simply equal to Vi minus VOS2 by A plus 1. Okay, so obviously the effect of this offset is not completely cancelled, but that is also suppressed by a factor of A plus 1. Okay, so we have the preamp here and the latch, right? If the latch has an offset, which I model it like this, say that is on the OS, and this also has an offset VOS2. Okay, and if the latch, sorry, and if the preamp gain is A, then the overall input referred offset is simply VOS, that is the offset of the latch divided by the gain A of the preamp, right? And we have plus or minus VOS2 divided by A plus 1, okay, where VOS2 is the offset of the preamp itself, right? So let me draw the circuit again. So we have input here and the preamp like this. I'll also show the offset here. We have it in feedback like this, right? So let's say this is phase 2, this is phase 1. Okay, and this technique is called auto zeroing, right? Where we kind of zero the offset of this amplifier. Okay, and it's called auto zeroing because in the earlier times, people used to tune bias current here to make the offset 0, but now this zeroing the offset is done automatically, right? And ideally, what will be the output here? The output will be, if I call VA0, that's going to be roughly minus A times VA, right? Assuming that the offset here is suppressed a lot. Okay, but obviously, we don't simply want the comparator to make decision based only on VI. We also need to do this, right? VI minus some VREF, right? We want the comparator to make comparison on this quantity, right? So let's see how to subtract the reference from the input. And if you remember from the last class, what we did was to use a capacitor that was charged to the required reference voltage, right? And connected in series with the input. Okay, but now we see that we already have a capacitor here that we are using it to estimate and store the offset, right? So we can reuse the same capacitor for storing the reference voltage also. Okay, so in the phase phi 1, where we are actually estimating the offset voltage and storing it, we can simply connect it to the required reference voltage. Yes, it can be the positive or the negative reference. So I'll just simply call it some VR. Okay, so here we want it Vi minus VR, right? So this is phase phi 1, and during phase phi 2, this is the circuit. Okay, so this is going to be phi 1, right? And during the phase phi 1, what happens? We are connected here. The capacitor is connected to the op-amp output like this. Okay, and let's say if the op-amp has high enough gain, then this will be 0. This will be the offset VOS2. Okay, so the voltage stored across the capacitor here, that will be the OS2 minus the reference voltage VR. Okay, so in the second phase, when we put the capacitor in series with the input, we have something like this, right? So this is my input, and the capacitor here was charged to VOS2 minus VR. So which means this voltage will be Vi plus VOS2 minus VR. So this voltage will be this voltage plus VR, sorry, plus VOS2, because this is offset. So this is essentially equal to Vi minus V. Okay, so the output of the op amp will be minus 8 times Vi minus V. Okay. Now, although we have seen it only for the single-ended circuit, we can simply convert it to a differential equivalent. So the differential implementation will look like this. So in one case, we connect it to the positive reference. Say this is my positive input, VIP. And here we have the offset. Okay, so let me not show the offset now. It's okay. So this is plus, minus. So this is going to be phase 2. This is phase 1. Here we'll have the negative input. Let me draw it properly. This is phase 1. This will be VR minus, and this is another capacitor. So this will be the overall circuit. Okay, and these two outputs will go to the latch. So let's say these go to our strong arm latch. So it will do like this. So it goes and connects like this. So this is our strong arm latch active during the phase phi 2. Okay, and at the top we have the cross coupled or the back-to-back connected inverter. Okay, and of course we have two more switches to reset the output and the intermediate node voltages. Okay, so this also reset to VDD. Okay, I'm not showing that. I'll just simply show it like this. Okay, so this will be the overall circuit, right? This portion is the preamp, and this is our strong arm latch. Okay, and this preamp here increases the overall gain of this entire system, so that the probability of metastability is reduced. Okay, and also it helps to reduce the offset of the overall system. Okay. Now another approach to reduce the effect of offset, which is what is popular in the modern times, is to do calibration, where the idea is the following. Let us say we have a strong arm latch. Let me draw it quickly. So at the top we have the CMOS inverters. Okay, and of course we have two switches at these two nodes, right? At these nodes that I'm not showing it. Okay. Now in this strong arm latch, we have the offset, or in any latch we have offset due to the mismatch between these two halves, right? Now the idea in calibration is to make sure that we add some additional currents to each of these branches, okay, so that we kind of counter this imbalance or this mismatch, right? So one way to do is the following. We can have a block here added in parallel to both these. Okay, and these blocks will add additional currents, okay, to these two halves, so that the total current flowing here, that will be matched as much as possible, right? So inside this block, we can have a structure like this, where we'll have multiple transistors. Okay, so they'll take in currents, right? And we can turn them on or off depending on the mismatch we have. Okay, so overall we have an optimal number of current sources on either sides, so that the currents flowing in these two branches are made equal. Okay, and the usual way is to have them sized in a binary weighted fashion. So let's say this transistor has a width W1, This will have 2W1, this is 4W1, this is AW. Okay, I'm just showing 4 transistors. So all of them are connected like this, right? And their gates will be connected to different voltages. So let's say this is some, V4, V3, V2, and V1. Okay, if these voltages, if the gate voltages are high, the transistor will be on, right? And it will start to draw current. Okay, and if it's 0, the transistor will be off and it will not be in the picture. Okay, so now by turning on and off the correct number of transistors here on each side, we can counter the imbalance. Okay, and that's what is done in practice, right? And of course, this block here, if you look at it, what it does, it takes the inputs V4, V3, V2, and V1, which are essentially either 0 or VDD, right? These are essentially digital signals, and it converts into an equivalent current. Okay, so this is essentially a digital to analog converter. Okay, so this is essentially a DAC. So we have 2 DACs here. Okay, and we'll turn on the appropriate number of transistors in each of them to calibrate. Okay, and one way to calibrate is the following. We take the latch, okay, and short the inputs so that the differential input is 0. Now, ideally, if the latch has 0 offset, its characteristic will look like this, right? Where it will have a sudden jump at 0. Okay, so if the input is 0, the output can either be at 0 or VDD, right? But in practice, due to the presence of noise, it will toggle between these 2 values. Okay, and since the noise in practice has 0 mean, so the output ideally will toggle between 0 and VDD. Okay, and even if it doesn't toggle exactly for each cycle, if you fire the comparator and record the output, say for 100 times, you will exactly have 50 ones and 50 zeros. Okay. Now we can use this information, right, and try to correct for the offset. So what we can do is we can short the input and look at the digital output here, right? The comparator output, have some logic here that will control both these DACs. Okay, and one way is to do the following. So let us say when you short it, due to offset, the output is at VDD, right? And let's say this is the output I'm monitoring. Or let's say, let's say this is the output I'm monitoring. Okay, so this is at VDD, right? So which means this half is slightly stronger, right? So which means that I need to turn on currents here, that is in this DAC, so that the currents here become higher and they match the currents here. Okay, so you try to switch on, transistors one after the other, and see when the output finally does like something like this, right? Or you capture it for 100 times and say, and find when it satisfies this condition of equal number of ones and zeros. Okay, and this is called foreground calibration, right? Because when we are actually doing this calibration, we cannot use the comparator or the latch to compare the input with the reference, right? Because here we are essentially shorting the inputs. Okay, so when we are doing the calibration, the latch is not available for use. So this is called foreground calibration, wherein before applying the input, you calibrate, right, and fix the mismatch issue, and then apply the input. And remember, this has to be done for all the comparators in our Flash ADC. Okay. Now we can follow a similar procedure to counter dynamic offset also, right? And remember, dynamic offset occurs due to the mismatch in the capacitors, right? So let's say these are the cross-coupled, the back-to-back connected inverters. Okay, and we saw in the last class that mismatches in these 2 capacitors will what? Result in dynamic offset. Okay, so now we can have a bank of capacitors on either sides, right? So this can have a bank of capacitors like this. Okay, so let's say I'm showing 4 capacitors for simplicity. So again, a usual procedure is to weight them in a binary weighted fashion. So this can be some C0, 2C0, 4C0, and 8C0. Okay. Similarly, here also we have the same structure. Okay. And you can obviously put, a combination of these capacitors in parallel, okay, on either of the halves to counter the mismatch in the capacitors. Okay. So that's about dealing with offset in comparators. Okay, so now let's look at the Flash ADC once again. So this is our Flash ADC where we have multiple comparators, right? And here we saw how to implement these comparators and saw how to tackle the offsets. Right, so now let's look at how the output of the Flash ADC look like. And let's say for simplicity, I'll take a 3-bit case where I'll have the input getting compared with 8 reference voltages. And let's say they are 1/8 of a VREF. I'll just show it as 1/8, 2/8. This is 3/8. Again, say 4/8, 5/8, 6/8, and 7/8. Okay. So let's say my input is somewhere here. Okay. So now remember, we have 7 comparators comparing with all these reference voltages. Okay. So this comparator will give an output of 1. This will be 1. This will be 1. This will be 1. Right? Because the input is greater than all these reference voltages. And here we'll have 3 zeros. Okay. But remember that ideally the equivalent binary representation we want is 4, right? 1 0 0, because this is 0 0 0, 0 0 1, 0 1. Oops, sorry. Oops. Anything below that 0 0 0, 0 0 1, 0 1 1. This is 1 0 0, right? So this is the equivalent binary we want, but we see that the output we have is looking like this. Okay, so this essentially consists of a string of zeros and string of ones. Okay, and this kind of a code is called a thermometer code, right? Because this looks like the level of mercury in old time thermometers, right? So if the input is increasing, we'll have more number of ones, right? So it looks like the level of mercury is rising in a thermometer. Let us now see how to convert this thermometer code to this equivalent binary code. So let's say the thermometer code we have is this, where we have 3 zeros and 4 ones, the same example we considered before, right? So one way to convert this to a binary code is to find where this transition from 1 to 0 is happening. Okay, and to do that we can use a simple digital logic, right? We'll take each comparator output and AND it with the inverted version of the previous of the next comparator. Okay, so we'll do it for all of them. Even for the last one, we'll do it. And for this, we'll assume that the output here is 1. Okay, the previous one is 1. So similarly, we'll do for everything. So similarly for this also. Oops. And for the top one also, we'll assume that we have an input 0 and that's getting added this. Okay, so this is this is this. Okay, now if you look at this output, all of this will be 0. Okay, and only this will have output of 1 because this is 0 and this is 1. Okay, all others will be 0, right? Now you can see that we have a total of 8 bits here, right? And in these 8 bits, only one of them is 1. And this essentially, if you code it like this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. This will be 1, 0, 0, right? And how to convert this 8-bit code to this 3-bit? Well, we can give it to a simple encoder, right? So we'll give this to an encoder that will convert this 8-bit input to a 3-bit binary equivalent output. Okay. But a modern solution to convert this thermometer to binary is to make the following observation. If you look at the thermometer code, right, we have a total of 4 ones, right? And the equivalent binary code is 100, which is 4 in decimal, right? So essentially, the equivalent binary code is the number of comparators that are produced an output of 1, right? That is simply the number of ones in the thermometer code. So one simpler solution is to take the thermometer code and give it to an adder, right? That is, you take all the 7 bits. So you take 0, 0, 0, 1, 1, 1, 1, and give all these bits to an adder. Okay. That will give the 3-bit output, right? And the most commonly used architecture for this adder is a Wallace tree adder, right? Because it's relatively faster and it's more efficient. Okay. Now, if you look at a Flash ADC, let us say we have a 6-bit flash. So which means we have a total of 63 comparators, right? So which means when you lay them out and place them physically, you will have the comparators placed like this, right? So you'll have all 63 comparators like this. Okay. So which means all these comparators must get the clock, right? And this clock obviously needs to be routed to a much longer distance. Okay. So to the comparator that is located at the farthest, the clock will come at a with a slight delay, right? For example, if this is the clock, let's say this is the clock here. Let me dot here. This is the actual clock that is fed externally. Okay. Now let's say this is the clock that is going to the comparator, right? That is the comparator at the farthest end. Let's say this is the comparator. This clock will be a slightly delayed version of this. Okay. Now we know that the falling edge of the clock determines the sampling instant, right? Now, if the input is changing very fast, okay, what will happen is the following. The comparators here, which get the clock without a delay, will process the input at this instant, right? They will take this sample and do the comparison, whereas the comparators at the farthest end, they will process this input. Okay, so essentially we'll be having a case where the multiple comparators here, they are not seeing the same input, but they are processing and doing the comparison on different inputs. So what will happen because of that is that ideally we should have had a proper thermometer code like this, right? But instead, we can have a case where we can have something like this. Okay. So this might happen because the comparator that is producing this output, right, might be processing a different sample, right? And this problem is usually called bubbles or sparkles. Okay. So obviously, if you directly take this as the output, there will be an error, right? So there are again a couple of solutions to tackle this. One is to not to trust the comparator outputs directly, but to look at the comparator outputs that are on either sides. Okay. For example, here, for this case, we look at the comparator outputs on its either sides, right? We see that on either sides, the outputs are 1. So which means we know that this definitely cannot be 0. Okay. So what we do is we take these 3 and find the majority. So for each comparator, we take the comparator outputs on either sides and find the majority of the three, and say that the output is majority of them. So for this one, it is this. For this comparator, we'll take majority of these three, and so on. And this is the majority of three encode. Okay. And this will obviously help us to solve when we have one bubble. That is when we just have 1 0 in between, right? So because if we have, let's say, 2 zeros or something, right? By visual inspection, it is obvious to us that these two must have been ones, right? But if you use this majority of three encoder, what we'll do, we will take for this one, sorry, for this one, we will take these three, right? And we'll see that the majority is 0, and we'll say that the output is 0, right? So majority of 3 will help us in only preventing one bubble. But another solution that will completely get rid of this bubble problem is to notice that all this problem is happening because the inputs that are processed by the comparators are different, right? This clock skew is something that we cannot prevent, right? Because if we have larger number of comparators, obviously there will be a skew between the clocks seen by each of them. Okay, so the inputs will be sampled at different times, but if we make sure that the input is held constant, okay, by putting a sample and hold or a track and hold upfront, right? So now, if this input is varying, this input will not, right? This might do something like this. Oh, let me just draw it properly. Okay. So now, if this is fed to multiple comparators, even if there is a skew in the clock, right? The input is held constant throughout the sampling period. So even if we sample here or here, the input is same. Okay. So this way, all the comparators will be processing the same input, right? All the comparators here, they'll process the same input. So we can get rid of this bubble problem. Okay. So if you look at a modern Flash ADC, they'll all have a sample and hold. Okay. And this sample and hold will be a very basic or a very simple sample and hold using, let's say, sorry, it may just consist of a simple switch and a capacitor, and it will be buffered using a source follower like this. Okay, and the sample and hold output is given to the multiple comparators. Okay, and the comparator outputs, let me draw the comparator also. Okay, and the comparator outputs are then given to an adder, which is usually a Wallace tree adder, and that will give us the binary output. Okay. And of course, each of these comparators here, they will have an offset, and to correct for them, we could either use a preamp, right? Or you can also do calibration. Okay. So let's stop at this point and continue from the next class.